class, today we're going to look at parametric equations. Again, this is an introduction to some things that you will probably be doing in Calculus 2. So let's look at parametric equations today. Okay, if you think about equations that we dealt with, we're accustomed to representing a graph by a single equation involving two variables, right? X squared equals 4y plus, that's a parabola. Today we're going to look at introducing a third variable into that, okay? 4x plus 2y, straight line, equals 0, straight line. We have x and y. So we're going to introduce that third variable, and we're going to call that a parameter, okay? So, where does this idea of a parameter come from? Okay, let us consider the path of an object that is parallel, or that is propelled. I can't read my writing. That is propelled into the air at an angle of 45 degrees. If the initial velocity is 48 feet per second, then the object travels a path given by the following equation: y equals negative x squared over 72 plus x. And this path that's being traveled looks like a semicircle. Okay, path looks like a semicircle. Which is a what? This is a downward pointing parabola, is it not? Downward pointing parabola. This equation, it tells us where the object has been, but it does not tell us the time that it was at a particular point. So, we introduce a third variable, t, and this is going to be for time, and we'll see that it doesn't necessarily have to be time, because in some of our problems we will bring in a third variable, theta, okay? But we introduce a third variable to this situation, t, and it represents time, and it is called the parameter, or called a parameter. And we can write x and y as functions of t to obtain a set of parametric equations. X equals 24 times the square root of 2t, and y equals negative 16 t squared plus 24 square root of 2t. Okay? So this is a set of parametric equations that represents introducing into what? This third variable t. So this and these set of parametric equations represent the same thing. We just brought in a third variable. Now what we're going to do today This is just introductory material, okay? We're going to give the formal definition for parametric equations, and then what we're going to do is eliminate the parameter, okay? You can go both ways where you are given an equation and you have to find parametric equations, but we're just going to, if given parametric equations, eliminate, and that's going to be a little easier for us to think about. So the formal definition of parametric equations is as follows. If f and g are continuous functions of t, on an interval I, then the set of ordered pairs is given by f of t and g of t. This set of ordered pairs is a plane curve. And this picture here was a plane curve representing that situation. It's a plane curve C. The equations x equals f of t and y equals g of t are the parametric equations for C, and T is the parameter. Okay? T is a parameter. So how do we go about eliminating the parameter? So in eliminating a parameter, we're going to start off with a set of parametric equations. And then we're going to go and solve for t in one of the equations. And then we're going to substitute into the other equation. And this is going to give us one rectangular equation. And this is what we're going to do today. Start off with a set of parametric equations, solve for t in one of the equations, and we'll see. Sometimes it's going to be a little bit more involved at this step than just solving for one, because we may solve, both for something. Substitute into the other equation, and then we'll get a rectangular equation. Okay? And as I said before, some of them will be a little bit more involved, but pretty much that's what we're going to do today. Okay? Pretty much we are going to eliminate the parameter for the most part. Okay? And we are going to find a set of parametric equations also, but that's going to deal with our conics once we get to that. So let's look at some elimination. First example, suppose we're given x is 3 minus 2t and y is 2 plus 3t. Now, we need to solve solve for t in one of these equations. It does not matter, okay? Your parametric equation may look a little different, but they should be equivalent. If I solve the first one for t, I have 2t is what? 3 minus x. So t is, divide everything by 2, negative 1/2 x plus 3/2 x. Okay? If I solve the first one for t. Then it says what? Substitute into the other equation. So I go over here, And wherever there's a t, I'll put my negative 1/2 x plus 3/2. And I need to do some simplification. I get 2 minus 3/2 x plus 9/2. So y is negative 3/2 x. 2 is the same as what? 4/2, right? 4 plus 9 is 13. Now, I'll accept this form of the answer. The book, however, is really going to get it to where they have a single line with 0. They're going to go, as I said, I'll accept this one. The book is going to go a little bit deeper and multiply everything by 2. And then they're going to go over here and get everything to one side. Okay? Either of these three, with me, would suffice as answers. But this is where your book is going to take it. Okay? So, we got rid of the parameter what? T. Got rid of the parameter T. Look at another one. This is a pretty straightforward one. X equals t, y equals t cubed. So if I do what? So one is already solved for t, so I put it where? Here. Y equals x cubed. Okay? Pretty straightforward. Okay? Any questions so far? Questions so far? Now, as I said before, you know, we say the parameter t. We're not going to look at where we have a parameter of theta. And we have to think about some trigonometric identities to help us eliminate the parameter here. Suppose we have x is 2 cosine theta and y is 3 sine theta. Now, we don't want to get into solving for theta. Doesn't mean we'll have an inverse sine or an inverse cosine. What we want to do is get this to a form that I can possibly use a trigonometric identity. Okay, I'm dealing with cosine and sine. Cosine squared and sine squared are related because the sum of that equals what? 1. So let me see if I can get to a cosine squared and sine squared and use the Pythagorean identity. Well, from here, I get that x over 2 is what? Cosine theta. And from here, y over 3 is sine theta. Right? Right? So knowing my trigonometric identity, that sine squared theta plus cosine squared theta equals 1, then I can properly say, and I'm going to write it, most times they want to write it with the what? X first, the x coordinate first. So we'll do x squared over 4 plus y squared over 9 equals 1. Okay? So that turns out to be what? Turns out to be an ellipse. So I may have to use some trigonometric substitution. Let's look at another one where I may have to use some trigonometric substitution. X equals cosine theta, y equals 2 sine 2 theta. Now, we cannot do what we did in the last problem. Why? How do those two problems differ? Here I have a double angle, okay? And there I just have a what? Single angle. So I really need to get that double angle down to a single angle before I can think about what I need to do. Okay? So and we have our double angle what? Formulas in the back of the book. Okay? Or in that sheet that you'll have access to. So how do I break this y down? Well, this 2 is already there. But sine 2 theta is what? 2 sine theta cosine theta, which is 4 sine theta cosine theta. So now I have broken these down to what? To single thetas. Now I already have that x is cosine theta, and I could put that there, but I still have that sine theta there. I still have that sine theta, don't I? How can I get rid of that sine theta? Well, I know that if I can get to a sine squared theta, I can substitute for 1 minus cosine, can I not? So you may have to in turn square both sides to get to sine squared, because all I know is x is cosine theta. So I can replace x with cosine to be fine. I don't know what sine theta is, but I can change sine to cosine if I have some squares there. So let's get some squares. Y squared equals 16 sine squared theta cosine squared theta. And from here, sine squared theta is what? 1 minus cosine squared theta. So I can put in my 1 minus cosine squared theta. And now I can perform some substitutions. Because cosine theta is x, so cosine squared theta is x squared. So y squared is 16x squared times 1 minus x squared. So it's not all about, solving for one or placing in the other. You may have to use some trigonometric identities. Okay? You may have to use some trigonometric identities.
Why could you, when you got the y equals 4 sine theta cosine theta, why could you go ahead and plug cosine theta into the...
You could have said x at that point, but you would have still had to try to do something for that sine theta. And for that, you still would have had to square both sides. And I mean, your x squared just would have been here already. You just would have substituted a little earlier. You could do that. You could do that. Are there other questions? All right, let's look at another one. X equals e to the 2t, and y equals e to the t. Okay, so I have x equals e to the 2t. Two ways you could think about this. I can think about x as e to the t squared. Can I not? Right? And what is e to the t? Why? Well, that's not the way I did it on my paper, but looking at what I did in this is simpler. So, I mean, what I did was I squared both sides here and then replaced x, but, you can do either one, but this was easier to think about. So, starting with one equation, someone else may start with the other equation and still get to the same parametric equation. One may be a little bit harder to deal with than the other, though. It may be a little bit harder. Okay. So we know that we can deal with some things here because we said what? This was an ellipse. So some of these parametric equations can give us the standard form for an ellipse, a hyperbola, a circle, or a parabola. Okay? What we're going to do now is we're going to do the circle and the hyperbola example, okay? And somewhere in your practice problem, you'll be looking at the ellipse and I think parabola, okay? But we can eliminate the parameter and get to the standard form for a circle. And we didn't get that in depth as far as graphing circles, but in the last class, we did talk about how to recognize whether something was a circle, right? So let's look at still eliminating the parameter. And this is a circle example. We have parameters. X equals H plus R cosine theta, and Y equals K plus R sine theta. And I want to eliminate the parameter to get the standard form for a circle. Well, it's going to be similar to this one, where I need to get to cosine and sine and square both sides, right? So how can I do that? Here, X minus H over R is cosine theta, isn't it? Here, Y minus K over R is sine theta. So if I do my cosine theta squared plus my sine theta squared over R squared equals 1, then I can get to the standard form for this circle by multiplying everything by what? R squared. And that is standard form for a circle. Right? Radius is the same. This is our center, HK. Yes, thank you. That should be squared. So, my set of parametric equations for a circle looks like that. So, now I know what that looks like. Let's look at an alternative example. Suppose we want to use this information to find parametric equations. For a circle. Now this is the first thing that we're going to be finding a set of parametric equations. But suppose that they give us, for this circle, that the center is the point -3, 1, and the radius is 3. So knowing that, based on the information from this previous example, I can find my set of parametric equations, can I not? Because my center is what? HK. So this gives me the equation for my what? Parametric equations. So X will be what? H plus R cosine theta.
The center of the circle is at -3 and 1.
And K, or Y will be K plus R sine theta. Okay? So now that I've done this, I can find a set of parametric equations for the circle if given the center and the radius. Okay? So that's our circle example.
What should do for circles that didn't have center and radius? Then be not possible.
They're going to have to give you some information to find it. They're going to have to give you that to find that set of parametric equations. Now what you're going to have to know is, by this lecture, what these equations are. And we're going to do, as I said, the hyperbola next. Your practice problems will be the other two. So you need to do those. And, find those, how to do the parametric equations. But they're very similar. Let's look at our hyperbola example. So now they're giving us X equals H plus A secant theta, and Y equals K plus B tangent theta. And they say they want us to eliminate the parameter and get it in standard form. Well, I have a Pythagorean identity dealing with secant squared and tangent squared, don't I? So let me get the secant and tangent. Well, X minus H over A is secant, and Y minus K over B is tangent. Now, I have that secant squared minus tangent squared is 1. So what's my secant squared? X minus 8 squared over 8 squared minus my tangent squared equals 1. And that is the hyperbola because it has that negative there. So notice these things come from these trigonometric or these Pythagorean identities. These circles, these hyperbolas, these ellipses, these parabolas come from that. So this is my equation I get when I eliminate the parameter. Now let's do it.
Where is it? We got the x minus x over a secant and all that.
We saw this for secant. Now let's look at an example of finding a set of parametric equations for a hyperbola. So this hyperbola, they give us the vertices to be plus or minus 2 and 0, and foci plus or minus 4 and 0. So I need HK and I need A and B. Or this H, I need H and A and K and B. That's what I need to get a set of parametric equations. What do I know about the vertices and the foci here? Being that the vertices is at plus or minus 2 and plus or minus 4, then what does that mean? The vertices are A units from the what? The center. And because I have no number in front of this, I know my center is going to be what? Yes, it is going to be the origin. It's the origin, 0, 0. The center is the origin. Because of this, HK is 0, 0. Because this is normally what? H plus or minus A, and so it is. Yeah, H plus or minus A, and this is K, 0. The foci, so this is what? A is going to be 2 because the vertices are A units from the center. The foci is what? C units from the center. Right? So I can find B. Now I need to have the correct formula for the hyperbola in finding B. Because I know with the ellipse and the hyperbola, those B squares and all that stuff, they're different. Those equations. So for the hyperbola, B squared equals C squared minus A squared. So B squared is 16 minus 4. So B is the square root of 12. So what's the square root of 12? 2 square root of 3. So what are my parametric equations? X equals H, which is 0, plus A secant theta, y equals k, which is 0, plus b tangent theta. Okay? And as I said before, you'll be dealing with, in your practice problems, the other two situations. Any questions? I take that back. You'll just be dealing with the ellipse situation. We're just doing circles, ellipses, hyperbolas. So you'll be dealing with the ellipse situation, which is very similar.
Where did the H go in the X equation?
Remember, H and K were 0. So it'll be 0 plus, but you don't have to write it.
Okay.
Center is 0, 0. Any questions about anything we talked about today? Y'all want to go ahead?
No.
Okay. This is the end of our talk on parametric equations today.